Okay, cool. So the recording started. Hi, we're talking about worksheet 3. Okay, cool. So let's start talking about question number 1. So the idea of question 1 and actually question 2 is to use the regular level set theorem. And I'll remind you what that is. Okay. So the regular level set theorem states, suppose f from n to n is a smooth map and q is an element of n is a regular value of f. And in case you have forgotten what regular value means, i.e., for all p in the preimage of q, the differential of f at p is surjective. That's what it means to be a regular value. And all of these points p here are called regular points, right? So a regular point is one where the differential at that point is surjective, and a regular value is something which contains only regular points in its preimage, right? So values, so just as like a general rule of thumb, when you're talking about these kinds of things, points are things in the domain and values are things in the codomain, right? So when you hear regular value, you're thinking something in the codomain. When you hear regular point, you think of something in the domain, right? Okay. Then the conclusion is that if the preimage of Q is non-empty, then that set is an embedded submanifold of M with dimension M minus dimension N.
So for this problem, because you want to use the fact that M is an embedded M-dimensional submanifold, so that is to say, there's a map from M into Rn that is an embedding. So everywhere its differential is in particular surjective. And then now, so you chain together that map with no, I don't know.
Yeah. But like you have the right idea, right? So so actually first, the easier examples of the regular level set theorem are showing that like Sn is an embedded submanifold of Rn plus 1. So like at the beginning of Lee's book, right, you show that Sn is a n manifold by constructing the charts explicitly, right? And then like you show that this is a thing. And then you talk about the regular level set theorem, and then he says, example, this is an n-dimensional manifold because it's just, right? It's just the norm function equals 1, right? And a lot of these examples where we calculate something using the regular level set theorem use the distance formula or the length of vector formula, right? So, and this is a really easy example, right? You just take the preimage of 1 under the, and normally, right, we square norm, because to quote Fred, all norms should be squared. That makes all the math a lot easier to deal with, because then you don't have that square root in there. But also you can prove that like SL and R is an embedded submanifold of either GL and R or just the set of n by n matrices. And for this one, you use the preimage of the determinant map at 1. Okay. Both the square of the norm map and the determinant map are just polynomials in the coordinates. So these are both smooth, and so you can just use the regular level set theorem to find these as appropriate embedded submanifolds. But when you're looking at a problem, anytime it's the dimension of the big thing minus a number, you should be like, how can I use the regular level set theorem to do this problem? It's a tool that's used in a class of problems. Okay, my cat. My wife isn't here to like distract her during class, so she's just gonna be sad and sitting next to me. Okay, so the idea is, and actually, this problem here is a problem that Fred has used on past final exams, is to show that SLNR is like, just show that SLNR is an n squared minus 1 manifold. Okay? And he doesn't ask you to show that it's an embedded submanifold, just like it's an n squared minus 1 manifold, right? And the way to do this is to use the regular level set theorem on the bigger thing. Okay, okay, so Rule had the right idea, is that since our condition is that the norm of V is equal to 1, so we want to construct G, which is going to be stuff composed with that norm, and take the preimage of 1 under that function G. And we want to show that 1's like a regular value and that this function is going to be smooth. But this is the idea. Okay, so how are we going to define G? That's right. Thank you, June. So let's let phi from M to Rn be an embedding. Define G, which is a map from the total space of M into R via the following composition. I'm going to take the total space of M, going to map it via the differential of phi to the total space of Rn. As given in the problem, the total space of Rn is just Rn cross Rn. Second thing that we're going to do is we're going to do projection to the second term. So we're just going to get 0 cross, or maybe projection on second term. Let's make that an on second term. There we go. And then here we're going to take the square of the length, or the norm. Okay. So it's a couple of steps that we need, right? And I'm sure that, right, if you had followed Raoul's line of reasoning of just trying to figure out like what do you need to pre-compose with the distance function, right, you would have gone here eventually, right? But the idea behind this is to recall what the definition, right, right, it's the set of all x comma v in the tangent plane of Rn such that x is in M, v is in Txm, and the length of v is equal to 1. And the only reason that I do this is because I want to define the length on the tangent plane of M, but like if I write this just assuming that I can take the length, then I could write it like this. And so this is why we do this projection onto the second term first before I take the length, because I want to make sure that I'm only taking the length on the second coordinate of this pair x comma. Okay, so now we note some facts. So the first is that phi is smooth. Since phi is, and the phi is injective, since phi is an embedding. And for this, you can see proposition 3.21 of Lee. Proposition 3.21 is exactly states that the total derivative, or the total, right, the total derivative is smooth. But the proof of this proposition also proves that the total derivative is injective whenever it's an embedding, right? It's the exact same steps, right? So I'm saying 3.21 of Lee, even though Lee only proves one of these two statements in this state, in that proposition, the proof works for both statements. So you can check there if you want details. The projection maps are smooth because why? What's the like one word adjective that Fred wants you to say to show that a projection map is smooth?
It's the zero map cross the identity, essentially, right?
Yeah, and so you could say like the zero map is smooth, the identity is smooth. So that would probably work. But the thing that I normally say here is that because it's a linear map, right? All linear maps are smooth, and there are tons of examples that Fred likes to use where you're trying to do this like smooth differential topology thing on a linear map. And then every time you're like, is this smooth? Of course it's smooth, it's linear. And the definition of being smooth is that it's well approximated by a linear map. Well, linear maps are well approximated by themselves, so linear maps are smooth. Okay. The last thing is that the square of the norm is smooth around 1 because
We can write it down and we know what it looks like when you take the Jacobian.
yes, what I was going to say, similar to the above, is I was just going to say it's a polynomial. Yeah, and polynomials are smooth, right? It's the square of the square roots that cancel. So you just take the sum of the coordinates square, or the sum of the squared coordinates, I think is the right way to say that. But that's just a polynomial in the coordinates. Right? Polynomials are always smooth. So, right? And so this shows us that G is smooth. Right? And then the last thing to note is that the pre-image of 1 under G is exactly the set UM. Right? So it suffices to show 1 is a regular value of G. Okay, any questions, comments, or concerns at this point?
I think you explained it, but if you could say it again. So we have to use the differential like in between, like before we use the projection, because we can't calculate like, I guess why can't we just take the projection directly from like the original set?
Yeah, good question. That's because in general, Tm is not diffeomorphic to M cross TPM. And this is true if M is covered by a single chart, as an example. But there are some examples that Lee gives as exercises where you compute the total space and you compare it to this space, and there's no diffeomorphism between them.
So is that like, so in this problem though, because it is, but you still want to move through that stuff, like just to be like general?
Yeah, so here saying this this actually isn't an equality, right? Not like a well-defined sense, because you have to like choose a pullback of the distance function for every tangent space, and that might not smoothly vary as you move across like different tangent spaces. So like that's why this total bundle is given as a subset of the total space of Rn. Yeah, so really we are taking this intermediate step because of the way that UM is defined, right? It's viewed when I look at the pairs of points on TRN and I take the norm of just the second coordinate of that ordered pair, right? And I just want to be faithful to that original definition. So I guess I should make this heuristic. Actually, there's a U somewhere in heuristic. I'm just going to put it there. It might not go there. I can't remember where it goes, but there's U somewhere in the word heuristic. Cool. Are there any other questions? Or maybe I didn't answer that question correctly.
And you have to finish it, right?
Yeah, so this problem still has a second part, but just questions up to this point. Yes. Yeah, but I wanted to take a moment to ask, because the only way I could think of to finish this problem was to invoke local coordinates and do like a local coordinate computation, but nobody likes to do local coordinate computations. And so I figured that like I'll take a moment to pause before we get to like gross parts. Okay. So, okay. Okay. So since the phi is injective, there exists a chart actually I'm going to squeeze, so I'm going to let P naught V naught be a particular element in the preimage of 1 under G. Just let this be arbitrary. We'll even say be arbitrary. So now I want to show, and I'll just write this so that way we can practice using the language, right? We want to show P naught V naught is a regular point. Okay. right? Because again, regular values are in the codomain, regular points are in the domain. Okay, there exists a chart, and I'm gonna even specify this slightly more. OneNote is a terrible program for taking notes, but I've been dealing with it for years, so I guess we're just gonna keep doing this. There exists a chart around P naught V naught so that dV of PV is equal to P1, P2, PM, 0, 0, 0, V1, V2, dot, 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 VM, 0, 0, all the way up to 0, right? Where here I have n minus m zeros, and here I also have n minus m zeros. Right, so this entire, and this is like the embedding level set theorem or something, or the embedding local chart theorem, or I don't know, there's a theorem that does exactly this, that says that like embeddings locally look like just projection onto the first m coordinates. And injective differentials are always embeddings because they're linear maps. So the differential of an injection is always injective. Okay. Sorry, the differential of an injective linear map is always injective because it's injective and it's linear. Okay, fine. Okay. Then, so this means that locally G of P comma V is equal to just the length of V squared, which is going to be the sum J equals 1 to M of Vj squared. And so here, this might be a little confusing, but remember that Vj is the jth coordinate of V, not V raised to the jth power. Jth chord of V squared. Okay, so now this is a map, or at least I can view it as a map by just viewing it as a map from my intermediary R n cross R into R, which is just a map between Euclidean spaces. And so the differential just coincides with the Jacobian. Right? So now we compute. Maybe I should scroll up one line just in case people are still copying. So now we compute the differential of G evaluated at P naught V naught, which is just i.e. the Jacobian. So the Jacobian is the differential of G with respect to my first coordinate. And each of these are evaluated at P naught V naught. But just for simplicity, I'm gonna, whatever the right word is, I'm not gonna write that in the notation, right? I'm gonna remove it from the notation just for like space reasons. But at the end, we're going to evaluate this at P naught. Okay. Differential of G with respect to P2, dot all the way to differential of G with respect to M. Then I have the differential G with respect to V1, differential G with respect to 2, all the way up to differential G with respect to Vm. And I'm just going to write evaluated at V naught out here instead of inside like you're supposed to. Okay.
Jacob,
Yeah.
what happened to the n minus m zeros?
So the domain of G is Tm, so it's a 2m manifold. So I should only have 2m coordinates in my Jacobian.
Okay.
Yeah, really the point of the 2n minus m zeros was to get this bound on the sum. That was a great question. Thank you for asking. Okay, so when I evaluate this, I know exactly what G looks like in terms of these coordinates now, right? It only has stuff to do, and maybe I should even write down what this looks like because it looks very nice, right? This is just V1 squared plus V2 squared plus all the way up to Vm squared, right? So if I take the partial derivative of this with respect to P1, I get 0. With respect to P2, I get 0. And I get zeros for all the P's up to Pm. Okay. And then the differential of this map with respect to V1 is just 2V1, and this is 2V2, all the way up to 2Vm. And this gets evaluated at P naught V naught. And so then when I do this evaluation, am I frozen? My mouse is like being super weird. Okay. Looks like I'm not. I still get all of these zeros. And then here I get 2V1 naught, 2V2 naught, all the way up to 2Vm naught. Okay, and then to bring us home, we say, since the length I want to erase this. Okay, it's not letting me erase for some reason, which is wonderful. Okay. All right. Technical difficulties. Oh my. So the end of this is going to say that since V has length 1, not all of its coordinates are 0. Therefore, this matrix is not the 0 matrix. And a matrix with only one row with at least one non-zero entry is a surjective linear map. Right? So therefore, the differential is surjective. And since P naught V naught was arbitrary, this shows that P naught V that 1 is a regular value. I do not know why this is not opening up my program again. But it's not. Okay. And now Zoom has like the spinny wheel every time I try to click one of the Zoom options. So it might be that Zoom crashes on me in like a minute. But it turns out that you can also solve question 2 using the regular level set theorem, right? You just take the distance from M as your function, and you use Sard's theorem to show that the set of critical values has measure 0. And since the critical values are exactly the values which are not regular, this means that like almost all values are regular values, including any sufficiently small values. Right?
Yeah, so once you said that we could use that, like you would want to use the regular level set theorem for that. That's what I was thinking of.
Yeah.
But then doesn't that not show the conclusion, right? The conclusion is that for sufficiently small epsilon, so you want to have that all epsilon close enough to zero, but there are measure zero sets that are dense around zero. So that you could conceivably have Sard's theorem telling you that at every rational distance from M, this is a problem, right? That it's at every rational distance, epsilon, there is the value, I don't know, d epsilon, d inverse epsilon could fail to be a regular set, right? Or epsilon might be not regular for all rational epsilon,
Right.
and this is not going to satisfy all sufficiently small epsilon.
Right. So maybe you would want something which is
Like, I might be recalling the wrong thing, but the picture I have in mind for how Fred did it was disgusting. Like, it was not a slick proof. Where'd he go?
He did say he thought Zoom was about to cut out on him.
Yeah.
While he's gone, could someone summarize what he said at the end of number 1 again, possibly?
Pretty
part?
sure we have it's a one row matrix, and the fact that it's not a 0 row means it has to be onto.
It's a rank 1 matrix, right?
Mhm.
Because it has a non-zero entry, because V is the vector V has length 1. So this matrix is rank 1 and is mapping to a one-dimensional space. So it's surjective as a linear map, right? Catherine?
okay. My computer is so bad right now that even Task Manager isn't responding. So I don't know what's going on. So sorry about that. Oh, and now it shows me in 2 places at once. Nope. Goodbye. Never mind. Okay, yeah, so it does seem like that you would want something better than Sard's theorem?
Yeah, like you dropped out right as I was mentioning this. If I'm recalling the correct thing that Fred did, like I don't remember any of the details, but Fred's proof, if I'm recalling the correct problem, Fred's proof was not slick. It's disgusting and requires a lot of like mucking about in details.
Yeah, unfortunately, this was the proof that Jonathan gave us when I took the topology qual prep seminar with him. And he was like, look, this is so great. And so the way that he interpreted it sufficiently small, which I thought was totally fine, was that for any real number r, there exists an for any positive real number r, there exists an epsilon smaller than r, such that this is an embedded hypersurface. And so that's how I, because I had no reason to doubt this, that's how I also read this question. Okay, good. We're still recording.
I mean, I'm fair with, I'm down with, potentially misinterpreting a statement that I can then argue to Fred, yeah, this is a valid interpretation.
Yeah. So that's how I've always interpreted this question. And by always, I mean like for the 2 months that I knew that this question existed before the qual, and then for like the 2 weeks this summer that I rethought about this question, it was, for any small value, you can find a smaller value that satisfies the condition. And that's sufficiently small, right? Okay. So we do only have 20 minutes left. So we could go over this question 2 with my solution, even though it might not be exactly what Fred's looking for, or maybe we can talk about one of the other 2 problems. It's up to you all. I switched to my laptop, but it's a touch screen, so we should still be able to talk about math.
I think for me, I'd actually like to talk about 2, even if you're gonna like that solution, you're not sure.
Yeah. Okay. Maybe then I'll just give an outline since I gave some technical details for the first one. So let me try to. That's not what I wanted to open. Oh, we'll make a new note here, and I'll try to figure out a way to combine these 2 PDFs when I upload the notes to the thing. So.
Oh, do you remember like which lecture Fred went over this by any chance? Because we could track down the video too to
Nope,
compare.
I remember this was one of the lectures that I just kind of zoned out on because it was ugly.
That's understandable.
If someone does find that lecture, let me know and I will cite it on the website so that way people can find the lecture easy. Okay, so.
I mean, I like this proof, even if it's like I feel like, this proof using Sard's theorem is great because if you're showing that, for all but a measure 0 subset, this works, that seems great to me. It's different than showing that in my mind, what I interpret sufficiently small epsilon to mean, but I'm fine with that conclusion as well. So like, I'd give that proof and just argue to Fred afterwards that, it's good enough.
Yeah. Okay. So let's just write out some steps here. So the distance function, which is a map from Rn cross R into R, this is smooth away from the diagonal, which I'll just denote as capital delta, right? Because the distance function, really the distance function is not a map from Rn cross R into Rn, it's a map from Rn cross Rn to the closed interval from 0 to infinity. But away from the diagonal means that I'm taking the distance function, remove the diagonal, and when I remove the diagonal, I just get an open interval from 0 to infinity, right? And so that's going to be smooth because the codomain is an open subset. Anyway, so that's the first thing. So then the second thing is that you're going to define G. And the reason that I keep using G for these metric-like things is because G is the letter that's used for Riemannian metrics. So there's a sense for where using G for a metric looks like a very natural thing to do. So we're going to define G of X to be equal to the distance between X and M. And this makes G a function, and the domain that we're going to define this on is from Rn set minus M into R. So this is also smooth because it's a restriction of the distance function to an open subset, right? It's a restriction of D to the open set Rn cross M, or Rn set minus M. And Rn set minus M is open because M is a compact submanifold. So it's a compact subset of Rn, and compact subsets of Hausdorff spaces are closed. That should be an exercises to know exercise. And if it's not, then I'm not doing my job very well. Okay, then 3, you say by Sard's theorem, the measure of the critical values of G is equal to 0. So by 4, the boundary of M epsilon, which is exactly equal to the pre-image of epsilon under this map G, right, is smooth, right, is good by regular level set for almost all epsilon greater than 0, including the ones that are small in the sense that I just stated. So let me zoom out so that you can see all the steps. Okay, I also have written solutions for all 4 of these, so I can post this solution document to the website after the meeting. Should I talk about 3 next or 4 next?
4.
Okay, and I'll probably go over just a little bit because I had the big technical issue, so I'll try to write down something for everything, but if people have to leave, then I understand. Although everybody did say that they were available till 12 on the when to meet. Okay, so let's talk about number 4, since I had one voice that requested it, and like a real life American democracy, that is a high enough percentage to decide what happens for everybody else. Okay, so the main idea for the proof of number 4 is that, note, for every element of my Lie group, the map L sub G, which sends G to itself, defined by left multiplication by that little element G, this is a diffeomorphism. So real quick, why is this a diffeomorphism? Well, it's smooth because it's a restriction of the multiplication map, right? And the multiplication map is smooth in a Lie group. That's part of the definition of a Lie group. And it has a smooth inverse because LG inverse is equal to LG inverse. And when I say that out loud, it doesn't sound like I said anything interesting, but when you look at where those inverse symbols are, that's the interesting thing. And then this is obviously an inverse map because if I multiply, right, by G inverse after I multiply by G, that's the same as doing nothing, right? So it's easy to see why both these functions are smooth and also why they are inverses of each other, and that's why it's a different morphism. Okay, so then we're going to let V1 up to Vn be a basis of, and actually, let me just specify a basis of derivations for the tangent space at the identity of G, right? So E is the identity of my group G. And the idea behind the rest of the proof is that I'm going to use these functions, LG, to push these basis vectors to all of the other points. And those are going to define vector fields, right? Because the definition of being parallelizable is that there exists a smooth frame, right? And a smooth frame is a collection of n vector fields such that restriction at every point creates a basis for the tangent space at that point. So we're going to define these vector fields. A collection of vector fields x sub I by xi at the point G is this thing. So what is this thing? This looks absolutely terrible, right? But this here, if I write it out, this is the differential of LG at the point E, right? So I'm taking a differential, right? And differentials, dLGE, right? This is going to be a map which sends tangent vectors at the identity of G to tangent vectors at little g of G, right? So this is exactly the map that I want to send the right tangent vectors at the identity to tangent vectors based at G. And so, you know, at this point, we've introduced a lot of letters and a double subscript, which is terrible, but keeping track of like what the subscripts are and what the subscripts are doing is like the hardest part, right? So note now that so at this point, I've defined a collection of rough vector fields. Maybe it's worth saying the word rough, right? But the definition of being a smooth frame is that the frame is smooth. So first I'm going to show you that it's a frame, and then I'm going to show you that it's smooth, right? So since LG is a diffeo, DLG, well, maybe the parentheses should go here. I don't know. No good place to put the parentheses. Okay. This map here is an isomorphism. Maybe I'll just say an iso. And so the image of this basis is a basis for the tangent space at G of M, right? Because that's exactly what linear isomorphisms are, right? If you've ever TA'd the Math 131 class here, and if you haven't, I highly recommend it. It's like my favorite class to TA. This is one of the characterizations that we give to the undergrads for the definition of a linear isomorphism. It's right. Linear map is an isomorphism if and only if it sends bases to bases. Okay. Then finally, note each vector field xi is smooth because LGH varies smoothly with respect to G. Again, it's the restriction of the multiplication map.
Probably silly. What do you mean by restriction of the multiplication map?
Yeah, so the definition of a Lie group is that it's a group G such that the functions mu, which send G cross G into G, where you send a pair GH to the product GH, and I, which is a map from G to G, where you send an element to its inverse, are smooth. And so here, if I want to say that this LG of H varies smoothly with respect to G, right, I'm just taking this multiplication map and I'm restricting the second coordinate to a single element H.
Can you explain again why that note each vector field xi is smooth because LGH varies smoothly with regards to G? Why does that second part imply the first?
Yeah, so basically you want to show that like if I choose a neighborhood around a point, that as the vector field moves on that neighborhood, right, that the choice of vector varies smoothly. Right? But our choice of vector is exactly right. So in like a super informal way, let's say that I move from xig and we move to, and like this is very informal, but I move to xg prime I. Well, how does that move? Well, I take L, the differential of LG at E of VI, and I move this to the differential of LG prime at E of V prime, right? And since LG prime smoothly, or LG smoothly transitions to LG prime, this means that, right, the LGE smoothly transitions to the differential of LG at E, right? So
And like in terms of like if we were to coordinatize everything and like just deal with Rn, right? Because we're dealing with C infinity functions when we say smooth. LG going smoothly to LG prime. Take the derivatives again, well, observe that all the derivatives had to be going smoothly. They couldn't have been any jumps or anything.
Yeah, yeah. Yeah, that's a good way to explain it if you like doing things in the coordinates. But I don't. So that's probably honestly the better way to explain it, is to deal with the suck that is the coordinate representation and do it. But yeah. Okay, and I know that I'm running out of time, so I'm gonna give an outline of number 3, and then we'll be done for the day. So if you have to leave, I understand. The recording of this will be uploaded after we're done. So the first, so here we go. Step 1 is to note the following fun fact. Note, if f from x to y is surjective, the mapping cone of f is just the cone of x with a relation where x01 is related to x11 if and only if f of x0 is equal to f of x1. Right. So basically, the idea behind this is that if your function's surjective, every element of y is represented by an equivalence class of some element in the cone. And so therefore, since I just want the set of equivalence classes, I can remove all of the elements of y without changing the equivalence classes, right? And since it's a disjoint union, I also don't change the topology. So that's the first step, is to simplify what the mapping cone of f looks like for surjective functions. And since all of these quotient maps that we're dealing with in the problem are surjective, this is an easier version of the mapping cone to use. So then in step 2, we have that note that the cone of Sn minus 1, this is homeomorphic to the n-disk via the map x comma t gets mapped to just x times t. And this one actually has a nice picture. So, right, the cone of, let's just draw the cone of S1 because I can draw the cone of S1. Right? So I have S1, and then I cross it with an interval, but I identify all of the points at 0 with a single point. Right? So here's 1, and at like 1/2, I have, you know, another copy of the circle that's sitting in there. But if I redraw this so that way that cone point is in the center, right, then this is just exactly, right, a disk, right? So the cone, we're like, here's S1, and here's S1, but the cone adds basically a smaller copy at every point, so you just get the disk D2, the closed disk D2. Okay. And you can even like think about how this works for like S2, right? You take the 2 sphere and you cross it with an interval and you get like a thick sphere, but then you identify all of the points on the outside with a single point. And you think, oh, well, the way to do that is to cross it with an interval that's going towards the center, and then that center sphere being a single point is exactly the same as being the 3 disk, right? So this is kind of nice. So this is a homeomorphism. And then in the third step, you just untangle these 2 observations, right? So the mapping cone of Pn minus 1 is the cone of Sn minus 1 modulo a relation, but this is the same as just the n disk mod a relation, right? Where x01 is equivalent to x11 if and only if Pn minus 1 of x0 is equal to Pn minus 1 of x1, but that's exactly the same as saying that x0 is equivalent to x1 if and only if x0 and x1 are on the boundary of the disk, and using the definition of the Pn minus 1 map, well, you're just identifying antipodes, right? It's a Z2 action. So you're saying that x0 is equal to plus or minus x1, right? But this is exactly, i.e., the mapping class, sorry, not the mapping cone of Pn minus 1, right, is exactly equal to Rpn, because Rpn is exactly equal to the disk mod the antipode on the boundary map, right? Like that's another equivalent characterization for Rpn, right? So in case you haven't seen this before, right? So like, what am I doing? Okay, right. So one way that you've seen RP2 is as the sphere with opposite points identified, right? X and negative X identified. Well, if I want to draw a simpler version of all these equivalence classes, I could just draw a disk where the interior of the disk is identified with itself, and the boundary of the disk is identified with its antipode map, right? So Rpn is equal to dn mod relation, where x is related to x for all x in the n ball, and x is related to negative x for all x in the n sphere. Right? This is another equivalent characterization of n projective real space, and that is exactly the definition that you recover from the mapping cone construction. Okay, so that's it for me for today. If you have any questions, feel free to stick around for a little bit. I have office hours tomorrow. Otherwise, I'll see you next week. I also, before you leave, I have written the next mock qual, and I'm going to upload that as soon as I'm done downloading the video and uploading these notes. Like when I update the website today with all of today's stuff, I will also upload the next mock qual. Feel free to take that as an actual mock qual if you'd like to, or just like try to do problems from it. Just like use it as like another problem list, as like a way to like practice doing a bunch more problems. We'll talk about those problems on Tuesday. There'll be no meeting next Thursday, so a week from today. I'm actually giving my oral exam next Thursday, right after this normal time. And I'm probably going to be too stressed about doing my oral exam in an hour and a half to do a qual seminar prep meeting. So I'll either add extra office hours or I'll add an extra day for us to meet before the seminar starts. That way we can make it the lost time. But yeah, that's what's going on there. So I'm going to go ahead and end the recording. So if you're watching in the future, bye-bye.